you very much for the kind introduction. And thank you all for being here. Thank you, Raul, for the invitation. So I'm pretty excited to be here, actually. And thank you, Christian, for setting this mini course. And so, yeah, so what's the plan today? So I hope that, so it's from here, sorry. Okay, so I hope that Christian already convinced you that non-Markovian models are very useful, or at least nature is non-Markovian, right? So a lot of processes in, I would say, and phenomena in economics and finance actually are characterized by inter-temporal dependence across time. And another way to see it is simply to say that things are happening at different timescales, right? And at least by the end of this, I would say first part, I'll try to convince you that there's a link between multiple timescales and non-Markovianity, okay, and also fractional bound motion. And so the first part today will be on fractional bound motion and more generally Gaussian Volterra processes. So I would say the continuous counterpart of what Christian showed you yesterday on Hawk's processes. So I have prepared some notebooks. There's a lot of material here. So I won't go through all of the, I would say, proofs step by step, but I keep them here just for you if you'd like later to have, I would say, something more complete. Okay, but I'll try as much as possible to give you the intuitions behind some of the properties, theoretical properties of these processes, and also we'll look at how to numerically implement, okay, and use them in practice. And this is usually, right, a very important step. I think here students in CAUS, right, are already familiar with this numerical implementation and the importance of the numerical implementation step, because this is usually where, okay, in theory, we have some convergence, I would say, a theorem, but when you move to practice, right, usually you need to be smarter, right, to implement things and make them work in practice. And this is what I usually try to tell my students is that, okay, you need to do this step. And this also allows you to get sometimes a better understanding on the theoretical aspect, right, of the process. And also we'll get back to this type of reasoning later, okay? So strong interplay between theory, numerics, and implementation, all right? And yeah, so this is just to highlight, right? You all know, I think, the infinite monkey theorem. So if you have a monkey that types randomly, let's say each second a letter, right? If you give it enough time, at some point it will write, for instance, all Shakespeare work, okay, without any single mistake. So this in theory, but of course in practice, you'll be long dead before this happened, right? And you don't want this, right, when you implement, let's say, some schemes numerically, you want them to, at least you want to find a way, right, to implement them in an efficient way, even if theoretically they converge, right? And this is a main issue, I would say, a main challenge when you want to implement these non-Markovian models, okay, even more than Markovian models. But we'll try to find solutions to that. And I also prepared a small homework for you to play with these processes and test by yourself. Also, I would say this phenomenon. Okay, so please, yeah, if you have any questions on the homework, I'm also here till Thursday, so don't hesitate to ask me some questions or even send me an email. Okay. All right. So some references are given here and also provided by the end of the talk, and we'll also, of course, provide you with the notebook. All right. Okay. So just to let's say go back to what we did yesterday. So here you have redfish. What's the particular thing about the redfish? It's pretty cute, but it has short memory, very short memory. Okay. On the contrary, if you look at shark, okay, It has longer memory. But the problem of shark, you don't want to be in front of shark, right? It's scary. Why are you scared in front of a shark? Because it's bigger, right? Okay, it's much more bigger than small fish, redfish, right? It's huge redfish, and this is exactly what happens when you deal with Markovian models, right? They're cute, right? Non-Markovian models, they're very big. Why? Because usually they're in infinite dimension. Okay, so you have the curse of dimensionality that hits you straight in the face. And with Christian, and I think Christian agree, what we'd like to show you, at least one message that we would like to convey in this course, is that they're not that scary. At least non-Markovian models are not as scary as they first look. Okay, and hopefully we can get both. I mean, the best of both worlds by the end of the course. And in fact, let's try to turn this point of view around, and let's maybe summarize the big picture that we try to solve, at least in finance, but also in other applied fields. So what are we trying to do essentially? We're trying to take optimal decisions based on some information that we have in stochastic environment, right? So essentially, we want to evaluate some quantities and optimize on these quantities, and usually, okay, they can be seen as some conditional expectations, right? You want to compute some conditional expectations with respect to the information that you have, okay? And usually, how do you do this? Well, depending on the information that you have, you try to rewrite this quantity as a function, right, of some important state variables that you have already identified, right? Usually, this is the first step, right? To construct good Markovian variables. If you do machine learning, it's called feature engineering, right? So you construct features to capture the available information, and even better, usually from the tractable point of view, if you're able to identify good, I would say, state variable that linearize the problem, then you get fast computations, right? Okay, and so if let's say we have identified these yn, and you can say, okay, if they linearize the problem, then f is linear, and you get a very simple problem to compute this quantity. And so even when you're in a Markovian setting, right, even if you're in a Markovian setting with a nonlinear problem, okay, there you might have an advantage to go to infinite dimension to identify good state variables that will linearize the problem. Okay, so you get more tractability. Yeah. And so instead of looking at dimensionality as a curse, I think we can look at dimensionality as a blessing. Okay, because it helps us linearize the problem, and we see this every day when you do deep learning, right? Dimensionality, neural network linearize the problem, right? Because the final layer of the neural network, you're just simply doing linear regression, right? So you linearize the problem. Okay. Okay, so this is the main message. So now let's get closer to the object that we're going to consider in this first part, which is Gaussian Volterra process. So just to fix notation and motivate, I would say, the next part, let's consider simply a Notion-Ullbach process X. So if you do finance, if you're interested in finance, you can use it, for instance, as a very basic block to construct short rate models, okay, where R will be the short rate. And usually you're interested in computing, again, some conditional expectations related to this process. So it can be this type of conditional expectation, which in finance corresponds to the price of a zero coupon bond. Okay, so basically it will be a product that will pay you 1 at maturity capital T. And what's really nice is that with a simple model, since you have a quadratic structure of something Gaussian, you can compute these Laplace transform in a way, okay, Laplace transform of the integrated square in an explicit form, okay? An explicit form, exponentially quadratic, and where phi and psi will solve a system of ODEs. I'll get back to these ODEs in the second part of the lecture, but for now, let's concentrate on the first part. Okay, on the modeling, I would say. X. So your X, Notion-Ullbach, it's Markovian. One very simple way to do it is try to extend it, try to include memory in X. Why we would like to do this? Because short traits usually, okay, are persistent in time. I mean, you have persistence, right, and long memory in short traits, so you want to include this type of, I would say, property in your model. And how can you do this? Well, by simply modifying a bit your Ocean-Ulbach process, you can include memory, right? So first of all, the Ocean-Ulbach process, we can write it in explicit form. We can write the explicit solution for the Ocean-Ulbach process. And conditionally on Fs, one particular property, interesting property of this process is that it's Gaussian. You can compute its conditional mean, right? And conditional variance, which is deterministic. Okay, so only the conditional mean is stochastic. All right, and of course, since the law, right, conditional law is Gaussian, it's entirely determined by the first two moments. This is deterministic, and you see, so the moment condition on Fs, the law of X is entirely determined by XS, right? So this means that our process is Markovian, all right? And this actually, we just showed that this satisfies the definition that Christian gave yesterday. And so this is Markovian, all right? Let's try to extend this to the non-Markovian case. One way to do it, and again, now I think you're familiar with showing with the seeing some kernels, right, appear in the dynamics. So basically, the idea is simply to replace, right, this guy here by a function G0, and this guy here for the exponential kernel. Okay, you replace it by a more general kernel K, all right? So you get to this type of objects. Okay. So you can take even non-convolution kernel here, right? And this is, in the first part, we will look essentially at the properties of this process. Okay, we'll see how it's related to fractional bound motion, for instance, and we'll look at some properties, theoretical properties, nice and bad properties, and then we'll look at some numerical implementation and simulation of this process. Okay, but before that, let's look at some examples. So basically, if you take a constant kernel or kernel that depends only on the S variable, okay, then you recover a Brownian motion with a time-dependent volatility. Okay, if you take the exponential kernel, you recover the Ocean-Ulbach process. If you've already heard about, let's say, Brownian bridge, it also fits into this framework, okay, for this particular kernel. And then you have fractional processes. I'll get back to this later. And you also have some delayed equations. Okay, so if you have an equation with some delay in the drift, you can actually rewrite it as a Volterra equation for some Volterra process, Gaussian Volterra process for some specific kernel, okay, that will be determined by the AK. Okay, so it's a bit more involved than for, I would say, the exponential kernel, right? Because if you only have, let's say, if you take TK equals 0, right, here, okay, and you take only, let's say, one delay, then you get back to the Ocean-Ulbach case. And we saw that the explicit solution, okay, can be written in terms of the exponential kernel in integral form, right? Same idea happens here, right? So you see, it's quite already a very simple object, okay? But already with the introduction of the kernel, you have a lot of flexibility, okay? Okay, so I mentioned fractional bound motion. Let's see how it's related to this object. So first, let's go back to the definition of fractional bound motion. So what's a fractional bound motion? Of course, there are several, I would say, equivalent definitions. One way to start is to say that it's continuous Gaussian process, centered, and that starts from 0 and has this particular covariance function. Okay, and the covariance function is entirely determined by some parameter h that we call the Hertz index. And you can check that if h is equal 1/2, okay, you recover the covariance function of the Brownian motion, so minimum of S and T. And so for h equals 1/2, you recover the standard Brownian motion, okay? And when h is different than 1/2, okay, you have this covariance structure. right? So in a way, it can be seen as a generalization of standard band motion. Okay, and this is what we call it, say, fractional Brownian motion. Okay, and it has a long history. All right. So if you go and check on the internet, you go to the Wikipedia page. Then Wikipedia will tell you that fractional band motion was introduced by Mandelbrot van Ness in 1968, but it's not actually true. Okay, so this is the English Wikipedia page, and if you switch to the French Wikipedia page, you get more accurate actually information. And this I noticed actually that when you switch languages in Wikipedia, it's not just translation, right? It's not just translation between two. So you can get two different, completely different pages, okay, for the same object, but in different languages. And in fact, so what the French Wikipedia page tells you is that, in fact, Mandelbrot van Ness actually popularized this object in finance in 1968, but it was actually introduced by Kolmogorov in 1940. And it has another, Kolmogorov gave it another name, he called it Gaussian spiral. Have you already seen this? And why would you think this is called Gaussian spiral? Any guesses? Okay, take standard band motion. What can you say of the increments of standard band motion? They are independent. How can you visualize independence geometrically? Saying that two things are independent, saying that they are orthogonal, right? So you start from the first increment, you have the second, right? And the third one, right? And then you move in multiple dimension, okay? And so now Gaussian spiral means that the increments are actually, okay, you have spirals, so the increments will not be independent, right? They will be correlated. I prefer this name, right? But I mean, it's more, but yeah, so this is the history, okay, at least small snapshot of the history of fractional band motion. It was actually introduced by Kolmogorov, at least in 1940. Okay, so let's look at some sample path before studying the process. H1/2, this is standard band motion, okay? H bigger than 1/2, you get something smoother than band motion. H less than 1/2 seems that you get something that fluctuates more than standard band motion, okay? Okay, and unlike classical band motion, okay, so for H less than 1/2, the increments are negatively correlated. This is why you see these large fluctuations, right? Why is it smooth here? Because for H greater than 1/2, they are positively correlated. Okay. So this is one of the key differences with standard band motion. Okay, and now you can say, okay, but how did I plot these graphs? First answer is I used a package, fractional band motion package in Python. Okay, you can play with this. Okay, I'll give you the notebook. You can play with this package, and later on, by the end of the talk, I'll show you how we're going to simulate fractional band motion. Okay, so you can use the package, but we'll also hard code it ourselves. Okay, so this is how these graphs were generated, at least here. All right. I mentioned that fractional band motion is related to the object that I already introduced, Volterra. I mean, this object X with the kernel K. Why is this true? Because actually you have several equivalent representation of fractional band motion. Okay, you can represent it as stochastic integral. So we define fractional band motion as Gaussian process, right, with specific covariance structure. But you can actually also consider or show that it admits other types of representations. For instance, you have the Mandelbrot van Ness representation against a standard band motion D, okay, double-sided. And you see here, you have something that stops at 0, okay? Plus you have a convolution, okay, with this fractional kernel that appears between 0 and T here. Okay, this is one representation. Another representation of fractional band motion, you can represent it only with an integral between 0 and T, but now you need a non-convolution kernel to do that. You still have the fractional kernel, and then you have not so nice, I would say, function that appears here, okay, with the dependence on T and S here, okay. And actually, you see that in both cases, you see this fractional, at least kernel or function, if you want, appearing, okay, in both sides. Okay, you can say, okay, let's drop this part here, or let's drop this guy here, and simply consider more simpler, I would say, object, which would be simply this guy here, and this has a name. This is the Riemann-Liouville fractional bound motion. Okay, it's not exactly the same as fractional bound motion, obviously, because we took some chunk off, right, some parts, but as we'll see, okay, it shares a lot of similar properties, okay, than that of fractional bound motion. In any case, with this representation here, or with this guy here, we see that we can rewrite the fractional bound motion represented as a stochastic convolution or stochastic integral with respect to some kernel K and standard bound motion. Okay, so it fits into the larger framework that we have identified earlier. And yeah, for the rest of this lecture, we're going to essentially concentrate on these types of objects for different kernels K and try to see what's the impact on K on the properties of X. So first from the theoretical point of view, and then we'll move to numerics and simulation. So this is what we'll call a Volterra process. Okay. So first of all, you can say, okay, I take a kernel, I construct a convolution or integrate again bound motion. Am I allowed really to do it? Is the object well defined? Okay. So first of all, let's look at the deterministic case. Okay. So you take kernel K and some function F, let's say here. Which conditions on K do you need for this object to be well defined? So you have an integral, so you need some integrability, right? So if F is in L1, K is in some sense in L1 in S, right? You can make sense of this guy in L1, right? Now let's move, if you move to the stochastic integral, okay? Here, you need more integrability on K, right? L1 is not enough because we know from Ito theory that you need L2 integrability, okay? So this already will restrict the class of kernels that you can consider, but essentially here, for this object to be well defined, you need K to be in L2 in U, essentially, okay? So square integrable or locally square integrable, right? Okay, so what type of, let's list some examples that are square integrable kernels or locally square integrable kernels. You have, of course, the constant kernel, so you recover standard bound motion. You have the exponential kernel, obviously. You have the fractional kernel for h between 0 and 1, okay? And you have the gamma kernel. If you multiply, you dampen the fractional kernel by the exponential, okay? So essentially, okay, the fractional bound motion, obviously this will be the main object of interest here, falls into this framework when h is between 0 and 1, okay? Let's look at some convenient properties of X. So you can prove that X actually, so X, and let me go back to this formulation here. So in the construction of the Ito integral, okay, so this again, you have deterministic part times, okay, integrated against bound motion. So you know that by construction, okay, this is maybe you called it, I mean, sometimes at least in French, we call it Wiener integral. So you're not integrating stochastic process against bound motion, but simply deterministic function. Okay, and this usually has nice properties in the sense that it is Gaussian, right? So and this also holds, okay, when you take now, let's say double function in T and U, okay, this still by construction T by T you can apply the same construction, and this is a Gaussian process. Okay, so this is a Gaussian process, and again, as I said, I'm keeping everything here for later if you want to have a look. Let me just, yeah. So let's look at this definition. So recall that, what does it mean for process to be Gaussian? So we say that it's a Gaussian process if for every T1, TD. So every, I would say, mesh of time, okay? Every vector, YT1 taken at this discretization grid, YT1, YTD will be a d-dimensional Gaussian vector, okay? And the Gaussian process is entirely determined by two things. So Gaussian distribution is entirely determined by its mean, right, and variance. Gaussian process is entirely determined by its mean function. So now, okay, you have infinite dimensional, right, process. So it's determined by MT, okay, and the covariance kernel, all right, which is given here. And so with this definition, actually, you can prove that the Volterra process, okay, so first, okay, why do I call it Volterra? Essentially because the integration goes to only small t, okay, so it's in a way adaptive, okay, and Volterra was an Italian mathematician that looked at these kernels, essentially studied these type of kernels that in a way are lower triangular kernels, okay. Why do I say lower triangular? Because one way to, if you want to visualize the kernel, you simply discretize time, okay, and we'll probably use it later. So let's say you have a kernel KTS, okay. So TNS will vary in, let's say, 0t, okay. So what you can do, you can discretize time. You take, let's take T1, Tn. Let's call T0 equals 0, Tn capital T, okay. And basically what you can do, you can observe, you can look at this matrix, which is n+1 times n+1, okay. You can collect the values of k evaluated at different ti, tj, okay. And a Volterra kernel means that if s is greater than t, it's equal to 0, okay. So if you want to represent, if I call this guy kn, right, so your kn will look, so it will have 0 above the diagonal, okay, and here it's not 0. So in contrast, of course, you can consider kernels which don't have 0 here, okay, and this is what we'll call Fractional kernels, okay. But these are usually, I mean, you see here the problem is that if I do this here, so the integration will go to time capital T, and this means that X is no longer adapted to the Brown motion, okay, if I take a Fractional kernel, right? So that's why we consider essentially in finance more, I would say, Volterra type kernels, okay? All right, so this X here is a Gaussian process with mean function G0, because this is centered, okay? And covariance kernel, just by Ito's isometry, you can compute it, okay? So this is a nice property. First, for our process, it has underlying Gaussian process, a Gaussian structure, okay? And this can turn out to be helpful, right, for some computations, right? And of course, it's Gaussian, so you can have control on all the moments, but this I'm going to skip. And via the moments, actually, you can estimate also, and this quantity already appeared in Christian's slides yesterday, okay, or at least maybe the discretized version of these increments, okay. You can control these type of estimates, okay, for xt minus xs to the power p for any p. Why is this useful? So you can control it in terms of the kernel, of course. Why is this useful? Because by controlling this quantity for all p, actually you can say something on the regularity of the sample path of your process, okay? This is Kolmogorov-Chentsov criterion, and basically using this, and of course, depending on the smoothness or regularity, if you want, on the kernel, it will imply some regularity on your sample path. We already plotted the sample path of fractional Brown motion, okay, and we saw that for h less than 1/2, it seemed less regular than Brown motion, right? And for h greater than 1/2, smoother, okay? And this actually, you can prove it from here, okay? You can prove this and quantify what do we mean really by smoothness. And actually what you can show is that the process, okay, here. So I'm going to skip this here, right? Okay, so what you can show is that the fractional Brown notion will be continuous and even Holder continuous, okay, of any order strictly less than h. All right. So this means what? This means that if you take standard Brown motion, you're almost 1/2 Holder continuous. Okay, you're Holder continuous for any your Holder continuous of order 0.5 minus epsilon for any strictly positive epsilon. Okay, so it's almost 1/2 Holder continuous. For fractional Brown notion, it's almost h Holder continuous. Okay, so you see the lower h, the less regularity you have. Right, bigger h, the smoother the path gets. Okay. Okay, and so this is another nice property of these Gaussian process. Depending on what you put on the kernel, you can recover continuity of the sample path, which of course has to be contrasted with the process that yesterday Christian showed, right, which are Hawkes processes, which have jumps, so discontinuous path. Okay, so here we get the continuous analog of, in a way, the Hawkes process, okay, to include memory. Right. So these are two very nice properties of our process. Let's try to now, so you have Gaussianity and continuity. So now let's try to look at some not so convenient properties. Okay, and for this, we'll try to do the computations together, some of them, okay, just to gain some intuitions on this process. So let us fix a convolution kernel, all right? So we consider this object, okay, to simplify things, we take G0 equals 0, just to look at the properties of this stochastic convolution. And of course, K needs to be in L2, again, for this guy to be well-defined, all right? And now we'll try to study some not so convenient properties of this object. Okay, so I'll try to do it here. Okay, if you're interested, you can, you can do this as an exercise. I mean, we're going to look at some questions here, but there are more questions. If you're interested, you can also include it in the homework. But let's try to study this object. So first thing we're going to try to do is to compute the conditional expectation of this process. Okay, why? Because you know that conditionally on ft, okay, you know that xt plus h, right, is Gaussian. So this we already proved, right? This is Gaussian with the conditional mean, right? This object appears here, and you have a let's call it, so here it would be t plus h, essentially. Okay, and you have, I would say, a deterministic variance. Okay, but in order to understand the properties of x, at least, let's try to first to compute this guy. Try to compute this guy explicitly. Okay, because this is deterministic, so we don't have to care about it. This is stochastic. Let's try to understand this object. Okay, to see which type of properties we can deduce on x. All right. Okay, so how can we compute this guy? And here, let's see, we need some notations. So first, okay, to ease notations, I will denote the stochastic integral by star. So the integral between kt minus s dws. So I will just simply rewrite it in compact form like this. And you'll see in a bit that this will become quite convenient. And convolution between, more generally, between k and any measure L. Okay, I will denote it in this way. Okay, So first thing, let's try to derive expression for the conditional expectation. So xt plus h, what's xt plus h by definition, right? It's the integral between 0 and t plus h of k t plus h minus s dws. So usually Markovian setting, right? You split the integral in two between 0 and t plus h. Okay, and you recover xt plus something, right? So here, let's see how things go. So let's split the integral between 0 and t plus h. Okay, so condition on ft, right? Condition on ft, this guy is ft measurable, okay, right? And this guy has mean 0, right? It's centered. Okay? So basically, e xt plus h, condition on ft. Okay, this gives me this guy, and so essentially it's again a stochastic convolution, but now with the shifted kernel that I shift by h, right? So I can rewrite it as, if I denote by the shift operator delta h, I can rewrite it in this form, right? Okay. Okay, and now let's try to work on this quantity, okay, to get an explicit expression of this guy. And now the idea will be to try to work on the kernel k first, or the shifted kernel, to simplify this expression. Okay, and this is where an object, at least in the study of deterministic integral equations, come into play, which is called the resolvent of the first kind. So what is the resolvent of the first kind of a kernel k? It's essentially a measure, okay, that allows you, in a way, to invert the kernel k. So basically, for the convolution operation, okay, in a way. It's not exactly true, right? Because it's not the identity function, it's just 1, right? But k star l at any s is equal to 1. Okay? So let's assume that the resolvent of the first kind exists. Okay, it's not automatic for any kernel, but for now, let's assume that such object exists, and let's assume that this quantity is differentiable. Okay, and now let's try to figure out an expression for the shifted kernel. Okay, let's try to show that you have this, and this you can do it. I mean, just one line of computation once you have this assumption here. So assume that this object, so this is a function, delta hk star l as a function of t. This is differentiable function. Okay, so this basically you can write it as the value is at 0, value of the function at 0, right, plus the integral of the derivative, right? But integral of derivative, let's say integral of a function fs ds, I can also rewrite it as the convolution of f with 1, right, with the 1 kernel, right? Okay, so here I have integral of the derivative of this guy, so I'll write it as 1 star delta hk star l prime. Okay, and now the trick is to use the property of L. You know that L star k is equal to 1. So basically what you can do is simply convolve on both sides by k. Okay, so if I convolve on both sides by k, okay, of course you need to justify that you can also do this in different order. And how can you justify this? It's simply Fibini. Okay, it's simply Fibini. All right. Okay, when you have, this is a constant, right? This does not depend on time. Constant convoluted with k, you can take out the constant outside, and it's 1 convoluted with k. Right? So it's 1 convoluted with k plus this guy. Right? And now observe you have this by definition of the resolvent is equal to 1. Okay, so you have 1 convoluted with this kernel, shifted kernel, 1 convoluted with k here times a constant, and you have 1 convoluted with this guy. Okay, so 1 convolution means the integral, right? So by simply inspecting the densities or the integrants, right, you can drop the 1 and you recover exactly this here. Okay. If you want, by simply differentiating the integral. Okay. Okay. I know that you have this computation. We can deduce an expression for the conditional expectation, because now you simply need to now that you have the expression for delta h of k, okay, you plug it in here. So let's plug it in here. So what is delta h of k? It's delta hk star L 0, it's a constant, right? Okay. Of what? Of k star dw. Okay, plus delta h k star L prime, right, which is this term, star k star dw. Again, it should be like this, okay, but using now stochastic version of Fibini, you can write it like this. Okay, and now what do you observe? Why is this useful? What can you say on k star dw? K star dw is x. So this is x taken at time t, right? So everything here is taken at time t. And here, this is x, okay? Meaning what? Meaning that the conditional expectation of xt plus h given ft so we have an explicit expression now for the conditional expectation. And let me write it in integral form now. That's okay. We use these notations, right, to simplify the computations here. Now let me go back to writing this in integral form. T minus s xs ds. Sorry? It's like a Jamel formula. Maybe, yeah, I don't know. Yeah, I'll check that, but maybe, yeah. Okay. And now what can you say on x? Yes.
From the past, it's not Markovian.
Okay, it's not Markovian. Might be. So it's not entirely true, because if I take k equal 1, okay, this is valid for any k, right? If I take k equal 1 or k equal to the exponential, we already showed that it's Markovian. I mean, you start from Brown motion is Markovian. But what happens actually in this case? So let's try to look at k equal 1. So example 1. K is equal to 1. Okay? Then what can you say on the shifted kernel? This is k h plus t. Since it's equal to 1, it's also equal to 1, right? Okay. And now what can you say on delta hk star L? Well, this is equal to k star L from here, right? But k star L, by definition, this is equal to 1. Differentiate this guy. This doesn't depend on t. So this means that this guy is 0. So you recover conditionally on ft. Condition mean only depends on xt. Okay? And condition mean determines the property of Markovianity of the process, right? So the whole law of xt plus h given ft depends only on xt. So this means that the process is Markovian. Okay, so actually this part simplifies in this case. Okay, and if you take the exponential kernel, again, we already know that it's Markovian. Okay. Example 2, take now kt equals exponential of minus lambda t. Again, shifted kernel. Now you get exponential of minus lambda h times kt, right? Because of the multiplicative property of the exponential. And now again, you do delta hk star L. This is, now you can take out this exponential, right? Because this doesn't depend on t, it depends on h. You can take it out of the convolution and you get k star L. But again, k star L is equal to 1 by definition. So you get this guy, which is independent of t variable. You differentiate it. This is 0. Again, it's Markovian. Okay. And if you compute this quantity, you get exactly, in this case, right, delta hk star L at 0. It's exponential of minus lambda h. So in this case, you get the known formula, right, for Auchin-Uhlenbeck process. You recover this, right? Okay. But in general, if this guy does not vanish, okay, what we just showed is that condition on ft, okay, the mean of xt plus h depends on the whole past up until time t of the process. Okay, so this means that the process is not Markovian. Okay, this is one way to at least argue non-Markovianity of the process. And this is first not so convenient property. Okay, so let's try to look at the second, maybe also not so convenient property. Yeah, so this I will leave it as an exercise. You can try to check, because for now, okay, everything we did was under the assumption that such a measure L exists. Okay, as exercise, I'll leave it to show that if you take a fractional kernel, then you have existence of this resolvent, okay, depending on the value of h. Okay. Okay, and these computations, I'll leave them also here in the notebook. You can get back to your computations. See similar type of computations. Okay, maybe not, it's not exactly what I did, but some hints for the answers. Okay. So now let's try to look at the second property. And so, of course, right, here we see that depending on the kernel, the process is Markovian or not, right? Now let's assume some smoothness assumption on the kernel, okay? So let's try to argue that if K is smooth, then the process is semi-martingale. Okay. And usually we like semi-martingales because, for instance, we can apply Ito formula to them, okay, right? So this could be a convenient property to have. Okay, so assume that, I think it's question 7. So assume that now that K, take K, let's say C1, okay? Okay, maybe to be precise, K differentiable with a derivative in L2 should be enough, but let's take it C1. Okay, C1 on 0t, all right? And let's try to show that X is a semi-martingale. So let's try to write an Ito decomposition for X. Okay, so you know that X, okay, if K is differentiable, you know that K, you can write it again as K0 plus 1 star K prime. Okay, and so your X, which is equal to K star dW. Now this is a constant, you can take it out, so you get K0 integral of dW, which means W, plus, again, okay, you see, it's very convenient to write with these notations because, and you get 1 star K prime star dW by Fibini. Okay, and this is where you need K prime to be in L2 to justify the Fibini. Okay, K prime is not in L2, you cannot do this here. Okay, it's just okay, technicality. Okay, and now you see X is simply constant times a Brown motion plus integral of something, right? So your X is semi-martingale, integral with respect to the S, right? So this shows that X is semi-martingale, and you can explicitly write the decomposition dxt, it's K0 dWt plus what's under the integral in the S here, let's write it explicitly, K prime T minus S dWS dt. Okay, so essentially the non-Markovianity, if it exists, okay, you feel it in the drift. Okay, for these processes. Okay, if K is in C1, right? Okay, so if K is in C1, you can show that it's semi-martingale. Okay. Actually, you can prove that for fractional band motion, except for the case H equal 1/2, it's not semi-martingale. Okay. So I'm not, okay, I did not prove this. I'm not going to give you full proof. Okay, but I'll try just to give you an intuition why fractional band motion is not a semi-martingale based on these computation here. Okay, we have all the ingredients that we need, and actually the actual proof is not, I mean, you get the idea on how you should do things, okay, from here. So what can you, so let's restrict to the case KT equal T to the power H minus 1/2 for some H between 0 and 1. This is the kernel that appears for the fractional band motion, or the Riemann-Liouville fractional band motion, if you will. Okay, now obviously this kernel, except for the case H equal 1/2, that you get KT equal 1. Okay, this kernel, okay, is not C1. Okay, except in this case. So of course I cannot apply this. Okay, but let's assume I can. Okay, apply this. Maybe you can shift the singularity of the kernel by some epsilon. You can write the semi-marking of the composition. Okay, so what does this tell us? Okay, so first let's look at H less than 1/2. So for H less than 1/2, what can you say on K0? Or the limit as T goes to 0. So if H is less than 1/2, this power here is negative. So this goes to plus infinity. Okay, so what does it mean here? It means that this guy goes to plus infinity. Okay, or more precisely, it means that you expect the quadratic variation of x to be infinite. Okay, and semi-martingale cannot have infinite quadratic variation, and this is usually the argument. Okay, that's used. Okay, not in this way, right? With this, but usually for H less than 1/2, you prove that fractional band motion has infinite quadratic variation, and thus it cannot be a semi-martingale. Okay, that's cool. Let's look at the case H greater than 1/2. Tell me, okay, now in this case, this is greater than 0, so K0 is equal to 0. I no longer have this problem. I have finite quadratic variation. I'm a semi-martingale. Not really, actually. Okay, you don't have a problem with this part, but what about this part? What happens here? So if K is greater than 1/2, so remember H is between 1/2 and 1, actually K prime, okay, differentiate once. This is no longer in L2. Okay, if it's not in L2, you cannot define this stochastic integral anymore. So what does it mean? It means that you have, so this term here for semi-martingale of the composition, this is the term that has finite variation, right? First variation. Okay, so this means that here you expect for this case to have infinite variation for the first term, right? Okay, so you have, if for H greater than 1/2, what do you have? For H greater than 1/2, you have now a process that has 0 quadratic variation, okay, but infinite first order variation. This cannot hold for semi-martingale, okay? At least continuous semi-martingale, right? For any semi-martingale, right? You have finite variation part plus quadratic variation. Finite quadratic variation part. Okay? And this usually, okay, just in 2 lines, this is usually the argument that's used to prove this. So fractional band motion, except for the case H equal 1/2, is not a semi-martingale, and it's not Markovian. Okay, so you can no longer, for instance, apply Ito's formula for fractional band motion. And it's not Markovian, so you need to keep track of the whole path, even if you want to implement things to simulate. Okay, we need the whole path. Okay, so these are not so convenient properties of fractional band motion, but let's now move to some maybe okay, which I collect here, but let's move to now the simulation part. I still have around 15 minutes or 15. Yes. Yeah, perfect. Okay. Okay, so I'll try to do some numerics in these 15 parts, or at least let's discuss now the simulation. Okay. And of course, in the, I would say tomorrow, okay, we will look at some processes, I would say, related to fractional bound motion, okay? And we'll see how we can actually derive some formulas, even in non-Markovian settings, to implement things in a fast way and be able to compute some conditional expectation in an efficient and fast way, okay? But today, we're simply going to look on how to simulate first the process, these Gaussian processes. So this is exactly, okay, the first part, how to replicate, I would say, the graphs that I showed you before on the samples, sample path. And then we'll try to look at the more efficient way of doing things, which will also give us additional insights on the structure of fractional bound motion. So first, let's look at the very, I would say, natural idea to simulate this process. Okay, so of course we have non-Markovianity, explosive kernels, but still we have very nice property of these processes here is that they are Gaussian. Okay, Gaussian processes, and Gaussian processes, you can actually simulate them in a very natural way using Cholesky method, right? So how do you do this? Since actually X is Gaussian, you start by, of course, discretizing time between 0 and capital T. You consider the vector, n-dimensional vector, X evaluated at T1, Tn. Since X is Gaussian process, right, you know that this is a Gaussian vector, okay? And you can explicitly compute its mean, okay? It's given by x0, so the mean of all these guys is x0 times the vector 1, 1, 1, right? So condition mean vector in Rn, and, or there's no condition, so mean vector in Rn, and the covariance matrix sigma, which is n times n, okay, and entirely determined by the kernel. Okay. Now, of course, depending on the kernel, maybe you can compute these integrals in explicit form, or you can numerically approximate these integrals. Okay, for fractional bound motion or Riemann-Liouville fractional bound motion, you can compute them actually explicitly, and for the true fractional bound motion, we already know, right? We have the expression for the covariance function. This is how we define it as Gaussian process. Okay. And with all of these ingredients, then all you have to do is actually simulate the vector of Gaussian random variables, okay, with a certain mean and covariance matrix. Okay. So how do you do this? You simply decompose the covariance matrix, either spectral decomposition, or more efficiently, you can do Cholesky decomposition. Okay. So by this I mean simply this linear algebra, okay? You start from sigma, symmetric matrix. You can actually decompose it. One way to decompose it, you can decompose it as a lower triangle, as a product, okay, of lower triangular matrix times its transpose, okay? So L is lower triangular, okay? And you can show very easily that this quantity, if I denote Z, now, if I'm able to simulate Z, n-dimensional IID, Gaussian random vector, okay, then mu plus LZ has the same law actually as X, right? Because it has mean mu, and what's the covariance? It's L transpose, which is sigma, right? Okay. And so basically, you compute the Cholesky decomposition. Once you have your Cholesky decomposition of sigma, you simulate Z. This you know how to simulate. You do matrix multiplication, you add the vector mu, and you have a sample path of your process X. Okay. Okay, and for the fractional bound motion, you already have an expression for the covariance function. So you can simulate fractional bound motion. Of course, the limitations of this is that It's usually slow, okay, depending on how fine you want your grid to be, right? Small n, the matrix becomes larger and larger. Again, for Cholesky, this might slow down things a lot. Okay, and it's specific to the Gaussian case. Okay, we relied heavily on the Gaussian structure. So if you want to apply it in more general setups, okay, it won't work. But what's really nice is that it's pretty easy to implement. Okay, what you need is just a function that computes covariance of fractional bound motion, for instance, and then you simulate by simply applying. So here you have, once you have the covariance matrix computed on the grid, okay, you do your Cholesky decomposition, okay, and then simply you do matrix multiplication of L times Z, so this displays the row of Z, and you get your path, okay? Okay, question, can you spot something suboptimal in the code? Let's say if you want to run a Monte Carlo simulation. And so you need to simulate a lot of path. So here for each path, actually, okay, I'm computing the covariance matrix and I'm computing the Cholesky decomposition, right? For each path. But these do not depend actually on the path, right? So I can do them outside, okay? And then, okay, maybe then you can vectorize also. And okay, but yeah, so you should take it out if you want to do Monte Carlo simulation. So this you can do it in the homework, of course. Okay, so sanity check against the package that I showed you before. So if you start from the same seed, actually, okay, using the two methods, you can check that, okay, you get superposition of this graphs, and of course, if you use different seeds, then path by path, of course, the comparison won't make sense. Okay. And for the homework, yeah, maybe you could also play with the Riemann-Liouville fractional bound motion, not the true fractional bound motion. Okay, so now let's move maybe to, in the final part, yeah, I have less than 7 minutes maybe, or let's see. Okay, probably I'll sum up and then maybe we go for a break. Yes, question. Sure.
For the Brownian fractional Brownian motion, the increments, the stationary process.
Yes.
Then
yeah, sure.
one.
This is a good question, but I don't think so. Yeah.
It's not
sure. But we'll look after the break at the more efficient method for that will also work for Riemann-Liouville. Okay. So I'll answer to this question after the break. Okay, so maybe let's sum up probably. Okay, this first part. So we looked at how to include memory in continuous processes, right? Through the kernel K, just simply by doing convolution, okay, of a time-dependent kernel. So the kernel that depends on TNS against random motion. You recover Gaussian process by doing this, continuous process, depending on K, the properties of K, regularity of K, you either get smoother or rougher path than random motion, okay, but it controls the regularity of the sample path. So these were two nice properties that we can exploit, for instance, for simulation purposes, right, using Cholesky. On the other hand, okay, it doesn't have. I mean, the main challenge of these processes, both in theory and in practice, is that they are in principle non-Markovian and some non-Semimarking. Okay, which makes it also more interesting object to study. Again, both from the theoretical point of view and numerical point of view. But I hope I convinced you, and with what Christian also showed you yesterday, that it's actually very rich and flexible class. Okay, already with a simple object, you can include some fractional processes. You have, of course, Orshad-Ullenbach process. You can include some delays, Brownian bridge, and so on. Okay, yeah, we have exact simulation using Cholesky. It's slow, very specific to the Gaussian case. But after the break, we'll look at a more efficient method. And as you'll see, by developing this method, you'll gain some insights, both theoretical insight and also practical insights on fractional bound motion. Okay, so it will help both from the modeling and theoretical point of view. Okay, so I think, yeah, I'm going to stop here, and I think we'll resume in like 30 minutes. Is this correct? Or... Perfect. Okay, and if you have any questions, I'm here. Thank you.
Okay, welcome back, and we continue with the second hour of the lecture.
All right, so as promised, we're going to discuss some more efficient. Okay, in this first part, we're going to discuss more efficient method for simulation that could also work when you have actually more general dynamics beyond the Markovian set. Okay, so I didn't say much about the extension, right, to non-Gaussian setting, where now you allow to have a even stochastic process here in the stochastic integral. Okay, and you can also have some more general dynamics in the drift. Okay, so we're not going to discuss these equations in details, but if you'd like, these are the analog of stochastic differential equations, but here it will be stochastic integral or stochastic Volterra equations. Okay, where actually you convolve the dynamics with a kernel. Okay, and you expect, right, that these type of or solutions for these type of equations would share the same properties that we already discussed, at least non-semi-martingality, continuity, and non-Markovianity in general, right? But yeah, so let's look at how to simulate more generally, I would say, these processes, but we will restrict, right, to the Gaussian setting and try to develop the method in the Gaussian setting. But what I'm going to show you also is still valid beyond the Gaussian setting. Okay, and let's try to do something that's more efficient than Cholesky, even in the Gaussian setting. So what's the idea here? And this actually idea, at least in our community, dates back to a paper by Carmona, Coutin, Montseny in the 2000s, but it's used in different fields. It's used in different fields, and it's difficult to keep track of the method, I think. And I think Christian also confirms this, because usually also they use different names for the same method, right? And it's very specific to every field. And I'm sure that, okay, once I describe the method, maybe also some people in the room also make links, maybe with similar methods in other fields. So please let me know, okay, if you've already seen it, in which fields and for which type of applications. So at least in our community, to the best of my knowledge, okay, always cite this paper. And then more recently in finance or for stochastic Volterra equations, a lot of works actually extend and adapt this method to our particular setting for, I mean, motivated by, I would say, applications in mathematical finance. Okay, so Christian has also very recent work on this with Simon, and there are a lot of people today working on this. Okay, so what's the aim? What's, I would say, the core idea of the method? The core idea is simply to restrict to the class of kernels, take convolution kernels, which can be written as some Laplace transform of some sign measure mu. Okay, this mu usually, okay, because we saw that the kernel K can have singularity at 0. Think of the fractional band motion. Okay, this is the main example that you want to have. The measure mu is not necessarily finite measure, but it has some integrability to ensure that K is in L2. Okay, so let's assume that we have this representation. And actually, this representation is valid. Let's look at some examples. For a large class of kernels. So essentially, if you take sum of exponential or one exponential, this already satisfies this relation where you take mu, the sum of weighted Dirac, right? Sum of weighted Dirac at some specific theta I gives you the sum of exponential kernels. Okay, so the sum of exponential satisfies this assumption. What's more interesting is that fractional kernel, okay, you can do the computation, you can show that the fractional kernel, all right, also satisfies this or admits this representation for this measure, okay, for fractional kernel with h less than 1/2, okay, so it's the less than 1/2 case, with this particular measure, which is now absolutely continuous with respect to the Lebesgue measure, okay. Completely monotone kernels, so basically functions, if you want, that are infinitely differentiable on 0 infinity open, so it can have a singularity at 0, such that the derivative switch sign can actually be characterized by this relation. Okay, this is Bernstein's theorem, if you've already seen it. So any completely monotone function can be written in this way. Okay, for now a non-negative measure mu. All right. So you see, it's already a large class of kernels, and sums and products of these kernels are also, I mean, sums and products of completely monotone kernels are again completely monotone, and so they will admit this representation. So it's not so restrictive, okay, class. So first, it's very rich class, at least in the class of convolution kernels. So let's see now how we can exploit this idea. Okay, so let's do some computation. Let's simply go back to our initial X, right, which is convolution, okay, kernel K convoluted with the dynamics of X. I will denote this guy by dz, all right? And now I replace K by this representation here, okay? And I apply Fubini. You interchange integrals. You have double integrals, right? Integral in time and integral, if you want, in space on the theta. You apply Fubini, and you get back to this representation. All right, so X, you're able to write it as some kind of weighted sum of factors that we call y theta. And what is y theta? By definition, okay, they are defined from X, at least from the dynamics of X, and they have this form. And in particular, for theta fixed, for fixed theta, right, you recover here the exponential kernel, so you recover semi-Marking. Okay, so for fixed theta, you can write even the dynamics of y. Okay, this is just similar to Orchan-Uhlenbeck process, right? So you have the mean reverting part, okay, plus then all the dynamics, dz, right? But dz, it's bx dt plus sigma x dwt, but x can also be entirely expressed in terms of the y, right? So this is b of x, right, and sigma of x. So you get homogeneous system in the y's, right? Okay, so why is this interesting? So first, let's try to understand what these y's are. Okay, so first, by looking at the dynamics, right, you see yt, 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 yt. So essentially, yt solves an SDE, right, and is Markovian. Okay, the system of yt, I make theta vary, right, is Markovian. they share the same dynamics. At least here, you see the y theta does not enter, it enters in a sum. Here also, right? So these two parts are the same. The only difference is that they have a different mean reversion parameterized by theta, right? So the yt, you can see this as family of process indexed by theta, okay, with different mean reversions. And what is x then? It's simply a weighted sum that can be infinite of these y theta, okay? So if I take mu, the sum of exponential, okay? If I take k, the sum of exponential, mu is just sum of Dirac, finite number of Dirac. So this means that x is a finite sum of finitely many y's, right? Okay. So this means that x, essentially, we're able to write it as Markovian in this y variable, which has finite dimensional, right? Because the system of y is Markovian, okay? Now, if I take a measure mu, which is now absolutely continuous with respect to the Lebesgue measure, which is the case, for instance, for the fractional kernel, how many factors y do I have? I have infinitely many, right? Because here you integrate over d theta, right? And so this means that fractional band motion, in a way, is Markovian, but in infinite dimension. We have identified, in a way, the variables that make fractional band motion Markovian, okay? Because we are able to describe fractional band motion as simply a weighted sum of these y theta, and for fractional band motion, b is equal to 0, sigma is equal to 1, so you can forget about the b part, and sigma you simply have dw, okay? And this also gives some insight on fractional band motion in the sense that you have infinitely many factors that are all constructed on dw, so they share the same band motion, so they are highly correlated, okay? The only difference is what is the mean reversion. So fractional band motion can be seen as an infinite superposition, okay, of Orchan-Uhlenbeck processes that mean revert at different speeds, right? And these mean reversions, since mu, right, is between supported, right, on R plus, these mean reversions, you have very slow mean reverting factors. And if you think of it, the very slow mean reverting process will, in a way, determine the level of the fractional band motion, okay? And then you have very fast mean reversion. So what does it mean to be very fast? So you have a process that is, if you take a very fast mean reverting process, you get very high oscillation and erratic behavior of the process. So in a way, these fast mean reverting processes can explain the roughness of fractional band motion, right? Because you're actually doing the sum of several processes that have very high mean reversion, and you see that fractional band motion can be seen as a superposition. Again, I mentioned different timescales at the beginning of the talk, right? And this one way to see that non-Markovianity is essentially can be seen, at least in the case of fractional band motion, as mixing different timescales, slow timescale and very fast timescale, right? And this, from a modeling point of view, right, this is interesting observation. So once you understand this, I mean, maybe you would like to add more timescales, additional timescale that you cannot maybe capture with fractional band motion in some configurations, right, and so on. So yeah, you can gain some insights. At least this is how I like to see fractional band motion. Superposition of different timescales, okay, with different factors that are correlated, highly correlated, but mean revert at different speeds, all right? Okay, and why is this useful now in practice? Now you see why it can be useful in practice, because if we stick to the fractional band motion case, okay, the y's are simply Orchan-Uhlenbeck processes. So if I'm able to simulate the y, all I have to do is aggregate them, right, and get simulation of x, okay? But the problem is that mu is Lebesgue measure, right? So I need infinitely many. So in practice, what's the solution is simply to approximate mu by finite sum of Dirac, right? Finite sum of Dirac, if I take n Dirac, this means that now I have to simulate a Markovian Auchan-Uhlenbeck vector in n dimension, okay? Now the question is, of course, how do we choose the weights, right? How do we choose the weights to approximate some specific kernel K? You can choose them in such a way that you minimize specific norm between Kn and K. For instance, take the L2 norm, and you take a geometric partition, okay, for the integral. Then you essentially can compute the weights of the Dirac, at least the point masses and the weights, right, for the Dirac in this way. That comes from the initial measure. So I'm not going to spend too much time on this, but you have everything in the notebook. And for fractional bound motion, what's really nice is that you can compute Ci and theta I explicitly in terms of H, okay? And then, of course, you have one parameter that you need in a way to optimize over the parameter to get a nice, I would say, approximation. You can prove that theoretically it converges, and then if you work a bit more, you can also get some convergence rates and so on. So everything is also in the references if you're interested in this. Okay, so this gives you a very efficient also way to simulate fractional band motion, but also more generally, as I said, stochastic Volterra equations. By essentially, you start first by discretizing the measure by weighted sum of Dirac. This means that xn will be weighted sum of some factors y, n factors, right? But which have Markovian dynamics. So you have a Markovian system here, and you can apply, let's say, standard Euler discretization scheme on this guy. Okay, although okay, standard Euler scheme will not eventually work because again, you get right. You see here, if you do numerical analysis, I mean numerical methods, you have several timescales to get some stiff system, right? And stiff system usually Euler. Standard Euler will not work. Okay, so you need to be smarter to decouple different timescales, right? And this is actually what you see here, right? So I'm not saying that it's easy. It's not just straightforward implementation, okay? But this you'll notice it also in the notebook, okay, in the homework notebook. All right, but again, okay, you can simulate this guy, and once you simulate this guy, once you develop the method for simulating this guy, which is Markovian, then you simply aggregate and get sample path of this guy. Okay, and just to show you maybe numerically, so if you take, for instance, the case of coefficients, so linear drift and square root for the volatility. So this is an example that we're going to look at tomorrow. At least the process, okay, that's generated by these type of dynamics. You see, if you simulate the factors, you see that the factors, so the color, so you have the small factor in light blue or almost white, and the fast factors or faster factors in dark blue. And you see, for one simulation, the factors are highly correlated, okay? And you have different timescales, right? So the lightish blue determine the level, they mean revert very slowly, and the darkest factors mean revert very quickly, okay? And this can be, in a way, responsible of the roughness, okay? Although theoretically, what's the regularity of the blue path? It's a Auchan-Uhlenbeck process, so it's Holder 1/2 regular, okay? Theoretically, it's Holder 1/2, okay? But practically, if you look at it, it looks rougher actually than band motion, okay? Unless you zoom in, right? Then you'll see the regularity. The regularity is 1/2. So you need to be, yeah. So it depends on the lens, right, and the time scale again that you're looking at. But for I would say realistic time scale with these fast mean reversion, you can in a way mimic roughness, right, and generate rough trajectories or rough processes with Markovian, okay, and semi-martingale model by simply taking fast mean reversions and fast also coefficients in front of these, so fast volatility, if you want. Okay. So this again, this from a modeling point of view also, this can help you a lot, right? Because once you understand that, okay, maybe roughness is just fast mean reversion and large vol of vol, then okay, if you want to implement things, let's start from a model where I include fast mean reversion and large vol of vol, so I don't have to deal. Let me implement the Markovian model and start with the Markovian model that have approximately the same properties, at least at the time scale I'm interested in, instead of implementing non-Markovian model. Okay, so also it can, right, again, so we go back to this point that by implementing things and working on things numerically, you can get some theoretical insights and also insights on how to model things, right? Also construct maybe more flexible models and more tractable models. So again, okay, once you aggregate these guys, as I showed you, you get sample path that looks rough, but again, theoretically, it's not rough. It's just, I mean, you're summing some smooth in a way. I mean, smooth path that have the same regularity as Brown motion. Okay, but again, you get something that looks rougher. And even if you want to estimate, so what Christian showed you yesterday, if you want to estimate the regularity of this path, okay, you'll get an H that is below 0.5. So even the H estimator of the Hurst index will not give you the correct value unless, again, you zoom in, you take a very fine grid, and then you'll see that the estimator will converge to the exact value. Okay, so said differently, if you take time series, if you have access to only finite time series of data, and you estimate the Hurst index of this data, it's difficult to deduce that this really comes from a rough process and not semi-Marking process, right? So, okay. But of course, so rough process can be a way to model it, right? But it's not the only way. And I think it's important to keep this in mind. So, okay, there's not the perfect model, right? All models are imperfect by definition. And you can use different models and they can have similar behavior on the timescales you're interested in. And again, I think it all boils down to the timescales you're interested in, okay, for your problem. Okay, so is there any question on this part before I move to the next one? Okay, so you'll get the notebooks in PDF and also Python format. Okay, so even if you don't have Python installed, you can still get the PDFs, right? And yeah, so let me move maybe to the second part now. Okay, so I think in the second part of the course, I mean, okay, to motivate it maybe and to make the link with what we just showed earlier. So on the graph, I showed you simulation of the square root rough process, okay, rough square root process, which we're going to study tomorrow. Okay, study some of its property and show that for some computations, you don't actually need to simulate it. Okay, you can do some computations explicitly or semi-explicitly. Okay, but in order to understand what we're going to do tomorrow, I'll need today to go back to the standard square root process, okay, or squared Bessel process, and try to look at some of its properties and how do we also use it in finance, okay? Because usually in these type of models, again, you lose Ito's formula, okay? You lose Ito's formula, and your Markovian models usually rely heavily. Markovian semi-martingale model relies usually on two things. You have Ito's formula, and you have PDE, right, methods that are quite strong. In the non-Markovian, non-semi-martingale model, so you lose both Ito's formula and PDE representation. And usually, at least my experience with these type of models, usually the trick, if you want to solve the problem in the non-Markovian, non-semi-martingale case, a good starting point is to go back to the standard Markovian semi-martingale case but try to solve the problem that you have without using Ito or PDE methods. Okay, so try to find a method, a strategy that actually have a chance to work in the non-Markovian set. So we usually need to go back and use very basic tools like Fibini and so on. And if you're able to apply strategy with these tools, okay, then there's a chance that you can extend it to the non-Markovian setting. And this is exactly what we're going to do here. So now I go back to the standard stochastic differential case. We'll try to understand it in a way that does not rely on semi-martingale and Ito, in a way semi-martingale, Ito, and PDE method. Okay, and tomorrow we'll see how we can generalize it to the non-Markovian case. Okay. So again, I'm interested in finance, and yesterday Christian mentioned the Black-Scholes model. So again, in the notebook you have a lot of information. You can have a look. So yesterday Christian mentioned the Black-Scholes model. What started it all, so even before Black-Scholes, it's just historical if you want to remark. It all started, mathematical finance started with Louis Bachelier in 1903. And he actually did his PhD with Henri Poincaré, okay, and he applied probabilistic method in finance and speculation. And actually his PhD was not well received by the mathematical community, because at that time probability was not really considered as mathematics, okay, unfortunately. And he really struggled to find a job, even in academia. So you can look it up, but it's very, very interesting story. Although his work, right, on using Brownian motion for modeling, let's say, stock markets, they were done, okay, maybe slightly before Einstein's use of Brownian motion, and they actually were recognized several decades later by Kolmogorov, okay, and they motivated theory of probability and so on. Okay, and maybe just a small remark. So what Bachelier did in his thesis was to model the stock price as simply drifted Brownian motion. Okay, Brownian motion with drift. Of course, it's not very realistic because Brownian motion can become negative. Okay, it's Gaussian, so it has a positive probability of becoming negative, right, at all time. And that's not very realistic for stock price. But you can use an argument if you start from S0 at time 0 positive, and you look at short timescales, the probability of this guy becoming negative is very small. So you could still make use of the Bachelier model. But in any case, Black-Scholes later on extended in some way this model to keep the process as positive, right? You now take, instead of taking shifted Brownian motion, you take geometric Brownian motion. But this is just small remark, and if you're interested, yeah, in the story and also some computation, everything is in the notebook. So here you see Black-Scholes, and I'm going to skip. Okay, so between Bachelier, Black-Scholes, and what I'm going to show you, there's of course a lot of progress that has been made in the meantime, but unfortunately I don't have time to tell you the whole story, but hopefully you'll find it in the notebook, and you'll also find also similar notions to what Christian showed you yesterday on the implied volatility and so on. Okay, but I'm going to, so as I mentioned, I'm going to concentrate on the square root process in SDE form today. And in finance, this was actually used by Hessen in 1992 to model the variance. So this is the equation we're interested in, SDE, okay, where you have linear dependence in the drift and square root dependence in the volatility, okay? And as Christian argued yesterday, he showed you that if you want to construct a model for the stock price, the volatility is usually stochastic, okay? And so this is a way of modeling stock price S with its stochastic volatility or variance V, and V is given in this way. Okay. And this is the most popular, one of the most popular models used, at least in finance. And why is it so? It's because actually we have an explicit solution for the characteristic function of the log price. Okay, which means that if you have access to the characteristic function, the characteristic function is you can see it as the Fourier transform of the density, right? So you have the density of the log price, which means that if you want to compute expectations of the log price, right, by Fourier inversion of the characteristic function, you get access to the density. Okay, and you can compute in quantities, right? So any expectation with respect to S, okay, if I know the density, I can compute it by numerical integration. But usually when you have an SDE, it's very difficult. I mean, you have a very nice way to describe dynamically the evolution of the process, but usually it's very difficult unless you have very specific configuration to explicit the density, right, of the solution of your SDE. And in this case, actually you get access to the characteristic function, which is the Fourier transform of P. So if you apply the Fourier inverse, P, okay, is the Fourier inverse of the characteristic function, which is known in closed form. You can plug it in here and do the computation without using Monte Carlo. Right? So this is a faster way, and more exact to compute these type of quantities without using Monte Carlo simulation. Yes.
Usually, maybe you keep it in the Fourier space.
Yeah, sure. Sure. So you are right, but you are entirely right. So when I say you do the Fourier, I mean, and plus you get two integrals. That's not the way to do it numerically. And if we have time, so we will provide you material on these Fourier formulas. And again, as Raoul mentioned, it's not the best way to do it like this, but we're going to give you. I don't think we'll have time to discuss the Fourier method and Fourier inversion techniques, but we'll provide you at least with a notebook, right, with some results, okay, on this, and on how to implement it also efficiently in practice, right? But of course, there's some work. So when I say okay, it's easier, but you still need to make it work. But this at least the intuition behind, okay? And this is what makes the Heston model popular. It's because we know how to compute the characteristic function, and I'm going to show you how to compute the characteristic function for this model. And tomorrow we're going to compute the characteristic function in non-Markovian setting that shares similarity with this guy. Okay, and I'll show you that we're going to use the same strategy as we did today. Okay, so actually Heston used PDE arguments to derive the characteristic function. Okay, maybe before I let me just check the time. Yeah, so before maybe quickly, I haven't said anything. Okay, this is an SDE, right? So first you need to argue that there exists a process V that solves this SDE. And it's not clear because square root is not Lipschitz. So you don't have global, it's locally Lipschitz, but it's not global Lipschitz. So you cannot apply standard global Lipschitz result to get existence of V. Plus you have the square root of V. So in order to take the square root, V, so the solution needs to be also positive or non-negative at least. And it's not clear, right, that you have the existence of a solution. But maybe to convince you, and again, in very particular setting, how to get a solution very easy. Again, in 2 lines, actually, you can construct a solution for this equation. So take a Norschan-Uhlenbeck process. Let's call it. So this, you know, it exists because you already seen that you can construct it as explicitly using the exponential kernel, right? Generate a solution and define Vt as xt squared. Okay. Apply Ito. So apply Ito to the square, right? And you get sigma squared here, right? Minus 2a xt times xt squared dt plus the part 2xt sigma dwt. And now notice that xt squared, by definition, it's vt. And what can you say on xt? So xt, not exactly, because x can be negative, right? But it's vt times the sine of xt, right? So I can replace it by 2 sigma square root of vt sine. Okay? So it almost looks like this. And by almost, you have this sign, right? Here. But now, let's call this guy dwt tilde. Okay? So wt tilde so what can you say on w tilde? W tilde is stochastic integral. Right? It's local martingale. It's against Brownian motion. It starts from 0. It's continuous. And the quadratic variation is t. So by Levy characterization of Brownian motion, W tilde is a Brownian motion. Okay? And basically what you showed is that you can construct a solution, okay, for the particular, of course, case where theta is linked to eta, right? You see the theta here is sigma squared and it's linked to this guy. So we constructed a solution for this equation. Okay? You can generalize the construction to take sums of other Orchellenbeck. Okay, and this is what we call squared Bessel processes. And of course, if you want to reach the result for any theta, this construction is no longer true. I mean, you need to work a bit more. There's a small subtlety here, actually, in this construction. So if you're familiar with strong solution and weak solution of stochastic differential equations, what happened here is that we started from V, right, or X, right? And the Brownian motion here, and the subtle thing is that the Brownian motion that we constructed W tilde, okay, actually depends on X, right? So we constructed a weak solution. We did not start from a Brownian motion and constructed a strong solution of V, okay? So V is not necessarily adapted, right, to this guy here. But then we need to argue that it is, right? In any case, this small subtlety here, but you can prove that you have strong existence and uniqueness by using, if you're familiar, Yamada-Watanabe, or you've seen it, Yamada-Watanabe type of argument. All right. So this is just to say that, at least convince you that you have a solution for this equation, okay? As long as theta is positive or non-negative. Why do we need theta non-negative? Again, also show you on just simple the intuition behind. So why do we need theta non-negative? To ensure the non-negativity of V. Okay, and how can you see this? Very easy. You start from V0, non-negative, right? And then you look at the first time you hit 0. Okay, if you hit 0, let's say here, this is Vt, right? And now write first order expansion of Vt plus h. So Vt plus h is Vt plus, you have the small increment, theta minus kappa Vt times h plus eta square root of Vt, and you have the increment of, so think of Euler scheme if you want, okay? And what this is telling you is that if Vt is equal to 0, okay, then this, and this, okay, will simplify, and so Vt plus h actually behaves as theta times h. So if you want the process to remain positive or non-negative, you need theta after you hit 0 to be non-negative, right? Because you want theta to push you back in here or to keep you on the boundary, right? If theta is 0. So this is just And this is usually the main argument on how you prove that this remains non-negative. Okay, you first put, if you want, the positive part or absolute value here, you construct a solution, and then with this type of arguments, you prove that this solution remains non-negative. Okay. But this is the intuition. Okay. Yeah, so I hope at least with this I convinced you. Again, it's not proof, but the proof is not far from this. Okay, at least it's the intuition of the proof. At least I convinced you that you have a solution and the solution is non-negative. Okay, so now that we are convinced that this is a well-posed equations, let's compute the characteristic function of the log price. Okay, so I'll give you. Okay, okay. For now, maybe we don't really care about these explicit formulas, but what we're going to show is that the characteristic function of the log price is actually exponentially affine in log S and V, where the coefficients phi and C are given explicitly. Okay, these are explicit, and this is what we're going to prove. Okay, because later again I'm interested in extending this to the non-Markovian, non-semi-martingale setting. And so this is well known since the works of Heston in 1992. Heston used actually a PDE argument, okay, because the model is Markovian in log S and V. Okay, you can write down the PDE, Feynman-Cat formula to this guy, right? You can write the PDE, and then he made a guess on the solution of the PDE, and he was able to derive these formulas. All right. The problem with this approach is that it highly relies on the PDE, which we're going to lose if we are in non-Markovian setting. So first, I would say challenge is to try to understand this derivation without using PDE method. And I'm going to show you that we can use probabilistic arguments to derive this. Okay, so we're going only to use probabilistic arguments to derive this expression. So let's try to do this here. Okay, so again, Heston is a combination of PDE plus a good guess. Okay, good guess of solution for the PDE. So here we're going to start with a good guess or ansatz for the characteristic function. Okay, of course, once you see the result, okay, I mean, you can make an ansatz, right? But we'll see tomorrow, okay, that how to construct a good ansatz. But here we start, so our aim, we fix some U in C. You can take it equal to IV if you want here, okay? And you want to compute the conditional expectation, so conditional characteristic function of this guy. All right. Okay, so you first start by making an ansatz. So yes, okay, because of the particular structure of the model, which I don't have maybe too much time to explain, you can start by saying that, okay, since the coefficients are affine, and by coefficients I mean the drift is affine and the variance, okay, if you square it, is affine, okay, there's some underlying affine structure. The characteristic function, you expect it to be exponentially affine in your Markovian variables, in your state variables. So you make an ansatz here, a guess, okay? Let me look for the characteristic function as some function phi t minus t. Okay, you can put small t only and then show that this is actually homogeneous because the coefficients of the SE do not depend on time. But I mean, let's just try it in this way. Okay, so this is a guess for some functions phi, psi, ki, deterministic functions, okay? To be determined, all right? So in a way, you decouple the stochastic part from deterministic part. And now the idea is, starting from this ansatz, you try to guess what phi, psi, and chi should look like. Okay, if you started, of course, from bad ansatz, this at some point, okay, would not work, right? But this is a good ansatz, at least in this particular setting. And let's try to see what we can say on phi, psi, and chi. So we assume that this is true, and our unknown here are phi, psi, and chi. Okay, so what can we say on phi, psi, and chi? So first, if this holds true for all small t, right? In particular, it will hold for terminal time when t is equal to capital T. Okay, so what happens if here in star I plug in capital T? So I plug in small t equal capital T. So here now I'm conditioning with respect to f capital T. This is f capital T measurable, so I lose the expectation. So we get exponential of u log st, which should be equal to the second part, evaluated at small t, so equals capital T, so I get this guy. V capital T plus key 0 log st. Okay, but this should hold true, right, for all capital T, right? And so this tells me that, and for all u, I mean not, so phi, psi, and chi, so sorry, so u is fixed, right? But this should hold true for all capital T, okay? And so necessarily, actually, if you want equality here, phi 0, psi 0 should be 0, right? So that you recover, and chi 0 should be equal to u, right? So by evaluating at the terminal time, you get some constraints on the value of the function at 0. Okay, so this is the first observation we can make. Okay. Second observation, now let's look from a dynamical aspect. Okay, because this holds true for all small t. Okay, and let me define mt, which will be the exponential of ut, where ut is this guy. So what can you say on m? Can you say something interesting on m? So first, what's the terminal value of m? M capital T, by simply our computations, right? M capital T will give you exactly exponential of u log st, right? Which is exactly the term here. So basically, if I go back to star, I have expectation of, I can replace this quantity by m capital T knowing ft. And if star is true, then this term, by definition, is empty. Okay? So if star is true, if my answer is true, I assume, then this tells me that m, that's why I called it m is a martingale. Okay? M is a martingale. If I apply Ito's formula on m, what do I expect? I expect the drift to be 0, right? So this implies drift of m is equal to 0. So let's apply Ito and make the drift vanish of m. Okay, so we can apply Ito because v is the same martingale, log s is the same martingale. And the dynamics of m, I can, okay, this is exponential. So this is just applying Ito to the exponential here, okay, here. And I need the dynamics of u. The dynamics of u, okay, are very easy to compute. So du here, right? It's, so I will drop maybe the t indices. So it's minus phi prime. I differentiate with respect to t, okay, minus c prime v. Okay. Let me first differentiate in time all my functions. Key prime log s. Okay. So these parts are in dt. So I have a lot of parts in dt actually. Okay. And then here I also need to plug in the dynamics of v. So I have dv, right? But I already know the dynamics of v. So I have c, the drift, it's theta minus, I think I called it kappa or lambda. I think it's kappa v dt, plus I have a part in dwt, right, which is eta c square root of v. Okay, these are the dynamics of dv and the dynamics of log s. So here I haven't written it in terms of log s, but let's take r equals 0. So your log s, so d log st, it's minus 1/2, again by Ito if you want, plus square root of vt dbt, and you have a correlation between v and w, which is given by rho. Okay, this is the model. This comes from the model, and so you can plug in this in here, and so you will get plus key times minus 1/2 of v, and you have Brown motion here, second Brown motion, correlated with the first one, times key. Okay, let's put it here, or let's drop this one. Okay, so this is the u. So I already have first part here, but I also need the quadratic variation. Quadratic variation of the u is simply this guy squared, but you need to take into account the correlation between the two Brown motion. So d, what is d u? This is simply the sum of the squares, right? And you see you have square root of v, square root of v. Okay, so you can factorize in any case v, and this is why I said we have affine dynamics, right? You see that you have some factorization in v. You have this guy squared plus key squared plus 2 times the correlation rho times d squared. Okay, so very simple. Okay, and now if you go back to m, I go back to m. I'm only interested in the drift part of m. So this is a part, this is in dt, right? This is a part in dt. I need to multiply by 1/2. Okay, and I only need to consider the part in dt here, right? So that I get the part in dt of m, because I know that the part in dt of m will be 0. Okay, so I want to make it equal to 0. So if I only look at the part in dt of m, I have 0 from one side. Okay, and then I have this plus this. Okay. But now observe that the dynamics are affine in v, right, and in log s. So I will collect the terms that are in front of v, or in front of log s, and then the terms that are alone. Okay, so 0 should be equal to minus v prime. Now I get back, okay, I'm putting the variables again. So I have this guy, which is alone, right? This guy is alone also, does not multiply v or log s, plus theta c t minus t. And I think this is it for the terms that are alone, right? And then we have terms that are multiplied by v. So of course I have minus t prime t minus t, minus kappa c t minus c, which comes from here. Okay. I also have this term here, minus 1/2 of key. All right. And we have all of these terms, right? So we have plus eta squared that I need to divide by 2, right? So key squared can enter here, right? Plus 1/2 of key squared t minus t comes from this guy, and here I have plus, I divide by 2, right, rho, which is linear in C. 2 rho T C T minus T. Okay, and plus I have the term minus T prime T minus T log ST. This is the drift, should be equal to 0, and this should hold true for all small t, right? For all small t, you can send, okay, for all small t and for all capital T. You send small t to 0, okay, and you see that actually you have an affine function. It's affine in V and log S. You have an affine function that needs, you can look at it as an affine function in V and log S. You have an affine function that needs to be 0 all the time. So this means that the coefficients need to be 0. Okay, so this gives you now equations on C. So first it tells you that T prime should be 0. Okay, T prime should be 0, so this means that T should be constant. T constant equal to its initial condition. So this tells me that T prime, so T of T should be equal to U for all T. So I already solved for T. Okay, but now T also enters here, but now I can replace it with U. Okay, and here I get the system of equation, which is phi prime should be equal to theta psi, initial condition phi0 equal to 0. Right? I also get psi prime now should be equal to theta squared over 2 c squared plus rho eta u. I replace key by u minus kappa psi plus 1/2 of u squared minus u, and my initial condition is c0 equals 0, which we already identified. Okay, so basically phi and psi need to solve a system of deterministic differential equations. Okay, and actually the equation for psi, so first you solve the equation for psi and you plug it back in here, right? This phi is just the integral of theta times c. So if you're able to solve this equation, then you get everything, right? And this equation, you have a nonlinear equation with a square, and this is what we call a Riccati equation, because Riccati, Italian mathematician, he actually studied these type of equations, and this is what we call Riccati equations. Okay, so first, before maybe discussing a bit more, maybe these Riccati equations, first of all, what's the result actually that we proved here by doing this? Do we get, did we prove this theorem here? Let's forget about these guys, but we did not actually prove this, right? So what we proved is that we assumed that we have this equality for some functions phi, psi, and chi. Then what we showed is that phi, psi, and chi necessarily have to solve these equations. Okay, so we did not actually prove that the characteristic function is equal to this. What we're interested in is actually in proving you need the other way around in a way. So let's try to go back, from here to here. Okay. Assume that you have a solution phi psi to the system of equations. Okay. Then from this solution, I can define my process M, right? Because my process M is defined from phi, psi, and chi, which exists. Right? What can I say on M? I can apply Ito on M. I can compute the dynamics of M, right? But since phi and psi solve these type of equations, the drift of M is 0, right? Same computations. Okay. So what can you say of a process that has drift 0? Local martingale. It's a local martingale. Okay. It's a local martingale. And then, so what I can say for now is that M, my process that I defined here, M is a local martingale. If in addition it is a true martingale, then what? Then I have this, right? But what do I mean? If I have this, what's the value of M capital T? It's exactly equal to this guy, because of my initial condition. So I actually prove this, right? Okay. So if we want to formulate, I would say, maybe let me write it here, what we just said. I'm sorry, where can I find the pen for? There's a good way to store the pen. Okay, so actually what we proved with this, so what did we prove? Fix U in C, okay. Assume that the system of Riccati equations, which I call R, so this will be this guy here. Okay, so assume that R admits a solution. A solution P and C that are C1. Okay. Then define MT, right, as exponential of phi t minus t, c t minus vt plus u log st. Okay, what can we say on M? Then our statement is to say that M is a local martingale. So if in addition it is a true martingale, so usually to move from local martingale to true martingale, you need some integrability, uniform integrability. If in addition it is a true martingale, then we're done. Then the characteristic function of the log price, which is exactly M capital T, is equal to M small t, but M small t is what we have, right? So this is the statement that we just proved here. Right? Do you all agree with this? Okay, so this is what we just proved. And so essentially, if you want to get the characteristic function, what are the missing steps? It's simply to verify that the assumptions that you made in this theorem. So first, you need to verify that indeed the Riccati system admits a solution. And what's really nice for these Riccati equations is that you can even solve the system explicitly. Okay, so your C is given in explicit form. You can check that by deriving this with respect to T, you get that C satisfies this equation. Okay, so you have the existence of a solution. So basically, this is holds true, right? If you take, let's say, U equals to IV, okay, with V and R, right? So this shows that this is true. And then usually the technical part is to go from local martingale to true martingale. Okay, and if you're familiar with this, you have an exponential local martingale. So usually one uses criterions known as Novikov criterion, but these do not apply here, unfortunately. So you need to work a bit more here. But actually, what you can show that your solution by working on the Riccati equation. For this particular case, you can show that the solution satisfies that the real part is negative. Okay, for all t. You can show that the solution for the Riccati equation satisfies this. And why is this helpful? Because actually now you can bound M very easily. Why? Because you're interested in taking the module, okay, of the exponential. So module of exponential, it's real part of C, real part of phi first, plus real part of C times V. Okay, if U is purely imaginary, this is equal to 1, right? The module of this guy. So you have to control this quantity. But now, under this information, this is negative. V is always non-negative. So this you can bound it with the exponential. You can bound it by 1, right? If exponential of something negative. And P is continuous on 0 capital T, so it's bounded, right? So all of this is bounded uniformly in T. And this is how you move from, you prove that local martingale is true martingale. Okay. And so this is how you can prove the characteristic function here using just probabilistic arguments. Okay, no PD, right? So tomorrow we'll try to look at the extension of this formula to a non-Markovian setting. Okay, and I'll show you actually that, of course, once you start from a good ansatz, okay, once you're able to guess a good ansatz, we're going to replicate the same argument. Okay, but of course you need to start from a good ansatz, and we'll see tomorrow how we can do this. How much time do I have left?
14 minutes.
14 minutes. Okay, so maybe unless Christian, you want to say something, so maybe I can. I could very briefly maybe show you an argument to prove the existence of a solution if it's not explicit for the Riccati equation in 3 lines. Also, it's very and I'll show you where this condition comes from. Okay. Okay, of course you can. If you have the explicit solution, you can here verify that real part of C is negative. But good luck with that. I mean, it's not. I mean, I haven't tried doing it, but I mean, yeah, you have square root of complex numbers and so on. I mean, maybe not. I mean, so I'll show you maybe by working on the ODE. Actually, you can get this in 2 lines or maybe 1. Let's see. Okay, so now is the difficult part of the talk, I think. So how do we slide? No, it's not here.
2 lines is
This one? Yeah. Okay, a little bit more and it will be up. Perfect. Okay, so let's say start from C prime. Yeah, maybe let's look at the Riccati equation. So usually, okay, if you want to solve this explicitly, usually you divide by C. Okay, first you complete the square. I mean, you have a polynomial here. Okay, so you factorize it and you divide by C, and this is how you're able to basically you decouple the equation and you get back to a linear equation. Okay, and this is usually how these Riccati equations are solved, at least in the 1-dimensional case. Okay, this is how you can obtain these formulas. All right, it's not what I'm going to show you here. I'm rather going to argue existence of solution for this type of equations. Okay, so usually how it's done, because you have quadratic dependence, so basically you can get finite explosion. I mean, explosion in finite time of the solution. So usually what you do is first you argue, okay, using known theorem, local existence of C on some 0 T max, and T max is the maximal time. So T max is such that so either T max is greater than capital T if we're interested only in solving the equation capital T, or you have that limit, you have divergence actually. So the solution, the local solution explodes before reaching capital T. Okay, so this is the, okay. So I'm going to use this result first, okay, to get local existence. But once we have local existence, then you want to argue global existence. So essentially, you want to prove that this configuration cannot happen, right? how do you prove this? Well, you simply try to bound CT, okay, on 0 T max, right? Okay, so let's try to bound CT. And here the trick, I mean, we like linear ODEs, so let's derive a bound. So here A, B, and C, okay, can be complex, but for simplicity, assume for now that A, B, and C are just real. Okay, let's solve the Riccati equation for real number, or else you need to take real part and do the same type of things, similar arguments, okay? But let's just simply show you the arguments for real part, or at least when A, B, C are real, okay? So you can rewrite it in this way, okay? And why is this helpful? Because let's say C0 starts from, or I can keep it C0. You can do variation of constant. Okay, so you can write CT as now. So I basically keep my C here, but I have linear part now in C, right? So okay, because of the square here, I can simply factorize it, okay? And I do variation of constant on this term. So basically the solution admits also this representation. So you have A, C, R plus B, and by the way, the coefficients can make them depend on time if I want, but C0 plus the integral between 0 and t of the exponential of the same guy, now which I stop at s. I think it should be between, I think it's between actually s and t. No, it's forward, so it should be like this. Okay, CR plus B dr. No, it's probably, sorry. It's probably from S to T. It doesn't. Okay, I don't know how to erase this, but it's probably okay. It's S to T, but this has very little impact. C dr. This is simply a variation of constant, so I get rid of the linear term if you want. But of course, C now enters also on the right-hand side. Okay, but why is this helpful now? Because, well, actually, if C0 is negative and C is negative, okay, exponential is positive, right? Exponential is positive, so this means this is always negative. So this is negative for all t, so I was able to prove this, right? One line, okay? But now we're interested in also bounding this guy. But once you prove that CT actually is negative for all time, if now you specify that A is non-negative, this guy is negative. I'm taking the exponential of something negative, I can bound it by 1. I can bound this guy by 1. And this allows me to bound C. So I get rid of my C on the right-hand side. And this gives me a bound on my CT, on the soup. And I get global existence, okay? Right? So, and this would be more difficult to see, I think, on the level of these equations, at least this part, right? That CT is negative. Okay, so maybe I can stop here. So tomorrow we'll discuss the non-Markovian extension of this model, and also we'll discuss some numerical implementation of these two classes of models with Christian. And thank you.
Well, before we leave, I wanted to give Christian and actually Eduardo something for the night work that they're doing in the course, right? And I didn't want to leave it for the last day of the course because people can run and you never know, right? So thank you very much, right? I'm very happy with the work you're doing.
Thank you very much. Thank you.